Solving linear systems symbolically. We just saw how to solve linear systems by graphing. We would graph the two lines and find the intersection point. Substitution and elimination are the two symbolic methods that we have for solving systems of equations. We're going to review the substitution method very quickly because it's usually the method that people remember pretty well, and it's the more intuitive of the two methods. The substitution method is a good method to use if one of your equations is already solved for a variable, like our second equation is already solved for y, or if it's very easy to solve an equation for a variable without introducing any fractions. So if it's already solved for the variable, then what we do is we take the other side. We have y equals 2x minus 6. What we're going to do is substitute this expression into the other equation for the y variable, because we're told that y is equal to this expression. What this does is it reduces our equation to a single variable so that we now have 3x plus 2 times y, but in place of y I'm going to put this expression 2x minus 6. Very important to put it in parentheses because the whole thing is getting substituted in for the y variable, and this is equal to 2. We now have an equation that's entirely in the x variable, so we can solve this for x and get it all the way down to a number, right? I'm going to distribute 2 into these parentheses to get 3x plus 4x minus 12 equals 2. Combining the 3x and the 4x in the same step, I'll go ahead and add 12 to both sides to move that away. That gives me 7x equals 14, and when I divide by both sides by 7, I end up with x equals 2. Now I'm not done at this stage because, as we mentioned before, a solution to a system of equations is an ordered pair. It's not just a value of x. So I have to take either of these original equations and substitute that value in. I'm going to choose to use the second equation, y equals 2x minus 6, because it's already solved for y, and that makes it a little bit easier to substitute in. So substituting in that 2 gives me y equals 2 times 2 minus 6, which gives me y equals 4 minus 6, or negative 2. So I now have my solution, which is an ordered pair, 2 comma negative 2. I'm going to put this in parentheses as my x and y. All right, so if our equation hadn't been already solved for y, we would have just started by solving for x or y, it doesn't matter which one, and then we would have proceeded from there. The thing about the substitution method is that, while it's fairly intuitive, the equation that we get is a little bit messy. So this equation was just a little bit long and messy, and that is much, much more true if you're not able to solve for a variable without introducing fractions. Once you start introducing fractions, these equations can really get quite messy, and then substituting back your fraction answer can get fairly messy also. And that's why we have the elimination method, which handles all those situations much more elegantly and without introducing any fractions. So we're going to solve this system of equations using the elimination method. And the idea with the elimination method is that we're allowed to add the equations together. Now, it's not helpful for us to just add these together in the form that they are currently in. What we want to do is add them together in such a way that's going to make a variable drop out. And we're allowed to do some basic modifications first. What I'm going to do, and I'll explain after I've gone through this one example, why I'm choosing to target the y variable and what this means. But first of all, let's just watch the example. What I'm going to choose to do is target the y variable. That means I'm going to try to make the y variable drop out. And the way I'm going to achieve that is by leaving this top equation alone, but multiplying through the bottom equation by 3. And that means I'm multiplying both sides of the equation, because if we recall from our techniques of solving linear equations, as long as I multiply that number by both sides of the equation, I haven't changed it. It's still the same equation, it's just written in a different form. So the top equation doesn't change, it stays 2x plus 3y equals 6. But the bottom equation, everything gets multiplied by 3, so that we have negative 9x minus 3y equals 15. And now I'm ready to add these together. And we can now see, when I add these together, 2x minus 9x gets me negative 7x. 3y minus 3y, these drop out entirely, and 6 plus 15 is positive 21. Now I have a very simple equation in x, which I can solve by just dividing both sides by negative 7 to get x equals negative 3. So, looking back now, I can see that I multiplied the second equation by 3 so that my minus y would become a minus 3y and that those y variable terms would drop out. And I can see why I chose to target the y variable instead of the x, because I could achieve that dropping out by just modifying one equation. Sometimes you have to modify both equations. Sometimes it's not really possible to make a variable drop out by just modifying one equation. So with the 2x and the minus 3x, I would have had to go for making both of those 6 and negative 6. I would have had to modify both equations. So generally we look for a way to just modify one equation, and if that's not possible, then we pick either variable and go ahead and modify both. Now, we're not quite done here, because as I mentioned before, a solution is an ordered pair. So far we only have an x value, but the way that we can finish this is exactly the way we finished the previous problem when we were using the substitution method. We can just take either of these original equations, it doesn't matter which one, 2x plus 3y equals 6, and plug that value in for x to find y. So that becomes 2 times negative 3 plus 3y equals 6. Or negative 6 plus 3y equals 6. When I add 6 to both sides in order to move that term over to the right, that becomes 3y equals 12. And I divide both sides by 3 to get y equals 4, so that my solution ordered pair is negative 3 comma 4. So let's go on to our next problem. We're also going to use the elimination method here. And if you're still kind of thinking that substitution is your favorite, I strongly recommend trying this system of equations with substitution, because it is not easy, and it's actually pretty easy to do by elimination. This time we could target x or y. They look about equally difficult, and so I'm going to choose to target the x variable, just so that we remember that we do have a choice. And since I'm targeting the x, I'm going to choose what to multiply each equation by based on what will make the x variable drop out. Looks like with 3x and 2x, I'm going to have to get one of these to be positive 6x and the other to be negative 6x. It doesn't really matter which is which, so I'll multiply the top one by positive 2 and the bottom one by negative 3. But it would work just as well to do negative 2 on top and positive 3 on the bottom. So this gives me 6x plus 4y equals negative 18, and negative 6x minus 15y equals positive 9. When I add these equations together as desired, I can see that my x variable terms drop out, and I get negative 11y equals negative 9, and then I divide both sides by negative 11 to get y equals 9/11. Now, I still need to go back and find x, and I can plug in 9/11 to one of these equations and solve it for x, but that's going to get just a little bit messy. So if we see that we get a fraction as our answer, and we know that it's going to be a little bit messy to plug it back in, there is another way. we can just start over with our 3x plus 2y equals negative 9, and 2x plus 5y equals negative 3. We can find y instead by just doing the elimination process again, this time targeting the other variable. So if I target y, that means I'm going to want to get these terms to be 10y and negative 10y. I'll multiply the top equation by 5 and the bottom equation by negative 2 to get 15x plus 10y equals negative 45. And on the bottom I have negative 4x minus 10y equals positive 6. Adding these equations together, I see that it has the desired effect of dropping out the y variable, and I get 11x equals negative 39. Dividing both sides by 11 gives me x equals negative 39 over 11. And now I can put these two answers together in a single ordered pair for my solution. This is negative 39 elevenths and 9 elevenths.